When we look from an evolutionary perspective, what we found is that in every species that we've carefully studied to date, sleep appears to be present, or something very much like sleep. What that means is that sleep must be essential. Sleep in human beings has actually been subdivided into two separate types. We have non-rapid eye movement sleep, or what we call non-REM sleep for short. And then on the other hand, we have rapid eye movement sleep, or REM sleep. And it turns out that these two types of sleep, non-REM and REM, will play out in a battle for brain domination throughout the night. So as we play out this sort of cerebral war of non-REM and REM, we can actually create a graph. It's actually called a hypnogram. So hypnos from a Greek derivative for the god of sleep, and then gram simply meaning graph. And that sort of cerebral war is going to be won and lost every 90 minutes, and then it's going to be replayed every 90 minutes. And what that creates is a standard cycling architecture of human sleep across the night. What actually happens as we go in and out of these different stages of sleep? Well, as we first start to fall asleep and we go into those light stages of stages 1 and 2 of non-REM sleep, our respiration and our heart rate just start to slow down. Our body temperature will start to drop. And the brainwave activity will begin to slow down a little bit. And then as we go into the deeper stages of non-REM sleep, stages 3 and 4, all of a sudden the brain erupts with these huge, powerful, big, slow brain waves. In fact, in the brain during deep sleep, for reasons that we still don't quite understand yet, hundreds of thousands of brain cells in your cortex all of a sudden decide to fire together, and then they all go silent together. It's this incredible physiological ballet of coordination. We have these sleep spindles that burst like fireworks on top of those deep brain waves. And those are synchronous short bursts of much faster brainwave activity, somewhere between 10 to 15 cycles per second. And if you were to listen to the brain, the deep, slow brainwaves are so rhythmical, you could almost slow dance to them. Non-REM sleep serves a whole constellation of different nighttime benefits for your brain and also for your body. Upstairs in the brain, non-rapid eye movement sleep will actually help strengthen and consolidate the information that you've been learning during the day. Sleep spindles, in coordination with those big, powerful brain waves, provide a file transfer mechanism at night from a more short-term vulnerable reservoir to a more permanent long-term storage site within your brain. And so deep non-REM sleep is going to help the brain capture those memories and almost set them in amber, as it were, so you're far less likely to forget those memories. We also know that it's during non-REM sleep, and particularly the deeper stages of non-REM sleep, where your cardiovascular system gets this cycling down, where your blood pressure starts to drop, and you switch over from more of the sort of activated, what we call the fight or flight branch of your nervous system. And deep non-REM sleep shifts you over into the quiescent branch of your nervous system. Fantastic for lowering blood pressure and lowering heart rate. We also know that it's during deep sleep that we improve our immune system function. And during deep non-REM sleep, we restock the weaponry in our immune arsenal. So when we wake up the next day, we are a more robust immune individual. It's not just that we increase the amount of those immune factors that are circulating in our body during deep sleep, but we also increase the sensitivity of our body to those immune factors. So you can think of deep sleep almost like the very best health insurance policy that you could ever wish for. REM sleep is dramatically different to non-REM sleep in many different ways. The first thing is that REM sleep is a remarkably active state. When we're measuring the brainwave activity during sleep at night, it's very fast and frenetic. Those brainwaves are going up and down many more times a second relative to deep non-REM sleep. In fact, there are some parts of your brain that are up to 30% more active when you're in dream sleep relative to when you're awake. And these are regions that control our emotions and our memories, regions that help our visual brain light up, regions that control our motor activity. All of these areas spark into life as we go into REM sleep, as we go into dream sleep. REM sleep seems to provide a collection of complementary benefits. It firstly seems to provide a form of overnight therapy. And it's during dream sleep at night that we take these difficult emotional experiences that we've had during the day, and REM sleep acts almost like a nocturnal soothing balm. It takes the sharp edges off those difficult emotional experiences so that we come back the next day and we feel better about those emotionally challenging events. So in some ways, it's not time that heals all wounds. It's time during sleep, and particularly during dream sleep, that provides this emotional convalescence. Indeed, it's also during REM sleep, during dreaming, where we take the information that we've been learning during the day and we start to integrate it and we associate it. REM sleep will seek out and test specific connections and associations between the recent information that you've acquired and all of the back catalog of information that you've developed across your lifespan. So you can think of REM sleep almost like group therapy for memories, taking information and seeking out and connecting these pieces of information. So when we wake up the next day, what we have is a revised mind-wide web of associations within the brain. And as a result, we can actually divine creative solutions to previously impenetrable problems that we couldn't solve when we're awake. How much sleep do we actually need? Well, for the average adult, the current recommendation is somewhere between 7 to 9 hours of sleep a night. And currently the CDC, the Center for Disease Control in the United States, stipulates a minimum of 7 hours of sleep for the average adult. But there certainly is a range of variability between that 7 to 9 hours. Some people may require more sleep. They may be closer to the 9-hour sleep need. But what we certainly know from the evidence is that the number of people who can survive on, let's say, less than 6 hours or 5 hours a night without showing any impairment, rounded to a whole number and expressed as a percent of the population, is 0. What happens to us when we start to fail to get the sleep that we need? So there is a global experiment that is performed on 1.6 billion people across 70 countries twice a year, and it's called daylight savings time. Now, in the spring in the Northern Hemisphere, when we lose 1 hour of sleep, we actually see a subsequent 24% increase in relative heart attack rates the following day. Yet in the autumn, in the fall, when we gain an hour of sleep, we see a 21% reduction in heart attacks. Isn't that incredible? And we see exactly the same profile for other things. For example, for road traffic accidents on our streets, suicide rates. Even we've observed this effect of daylight savings time and the loss of 1 hour on the harshness of the sentencing of federal judges. And so if you are sentenced the day after daylight savings time switch in the spring, you're likely to receive a harsher judgment because of the bad mood that judge is in because they've lost that 1 hour of sleep. That's how fragile both our bodies and our minds are with even just the smallest perturbation of sleep. I think many of us think very little about losing just 1 hour of sleep.